Hello my dear friends, you are most welcome in this beautiful lecture. In this lecture, we will discuss about the nucleophilic and electrophilic substitution reaction of aryl halide. Without the waste of time, let us start the topic. Take your pen and paper and start the topic. Nucleophilic substitution reaction of aryl halide. All of you know that aryl halides are extremely less reactive toward nucleophilic substitution reaction because there are many reasons behind this. Like number one is the resonance effect. Number two is the difference in hybridization of carbon atom in a CX bond, because the hybridization of carbon atom in aryl halide it is different, in alkyl halide it is different. Number third is instability of the phenyl cation, and the number fourth is because of the possible repulsion. So let us discuss these reasons one by one. You know that benzene, which is attached with the chlorine atom, has tendency to withdraw the electron, lone pair electron of the chlorine atom. So benzene withdraw the lone pair electron of chlorine toward itself and involve them in resonance, and you can see the structure of the resonating chlorobenzene. When benzene withdraw the lone pair electron of chlorine toward itself, it create ortho position electron rich, and after resonance para position also become the electron rich. So ortho and para position of the halobenzene become the electron rich, and you see the structure like this. It means the carbon atom of the benzene and the chlorine atom become the double bonded, which is a very strong bond. In haloarenes, the electron pair of the halogen atoms are in conjugation with pi electron of the ring, and the following resonating structure are possible. Now, CCl bond acquire a partial double bond character due to the resonance. As a result, the bond cleavage in haloarenes is difficult than haloalkanes, and therefore they are less reactive towards the nucleophilic substitution reaction. Now let us discuss about the second factor which make this reaction difficult. That is the difference in hybridization of the carbon atom in CX bond. In haloalkanes, the carbon atom attached to the halogen is sp3 hybridized, while in case of haloarenes, the carbon atom is sp2 hybridized, that is a double bond. You can see in the structure, the carbon atom attached with the halogen in haloarenes, that is sp2 hybridized, but in case of haloalkane it is sp3 hybridized. Now, the sp hybridized carbon with a greater s character is more electronegative and hold the electron pair of CX bond more tightly than sp hybridization carbon of haloalkane with less s character. Thus, CCl bond length in haloalkane is 177 picometer, while in haloarenes it is 169 picometer. You can see the shorter the bond length is, the strength of the bond become more as compared to the bond having more length. So it will be difficult to remove the chlorine atom from the benzene, and it will be difficult to show the nucleophilic substitution reaction. Now let us discuss about the third factor which make the reaction harder. That is the instability of phenyl cation. In case of haloarenes, the phenyl cation form as a result of cells self-ionization will not be stabilized by resonance, and therefore SN1 mechanism is ruled out. And the fourth one is possible repulsion is likely for the electron-rich nucleophiles to approach electron-rich arenes. So these were the reasons which make the reaction difficult. Now let us discuss about the another reaction of the halobenzenes. That is the replacement of hydroxyl group of chlorobenzene. We know that it is not easy to replace the chlorine atom attached with the benzene, but it is possible. When chlorobenzene react with NaOH, it will possible at a very high temperature and very high pressure. You can see the reaction. Chlorobenzene at 623 Kelvin temperature and 300 atmosphere in acidic medium, your product will be phenol. And if we attach the electron withdrawing group to the halobenzene derivative, like the nitro group at para position, the reaction is possible at the low temperature also. It will give you the para-nitrophenol. As the electron withdrawing group tendency increase, like if we attach two nitro group attached with the halobenzene at the ortho position and the para position, the reaction is possible at the low temperature, that is 368 Kelvin. The reaction is possible. It will give you ortho-para-nitrophenol. But if we attach three nitro group at both the ortho position and para position, the reaction is also possible at the very low temperature, that is on warming. It will give you TNP, trinitrophenol, which is the picric acid. You can see on your screen. This is the this is the picric acid, orthonitrophenol, 2NP, you can say. The effect is pronounced when NO2 group is attached, introduced at ortho-para position. However, no effect on reactivity of haloarenes is observed by the presence of electron withdrawing group at meta position. It is very interesting. So let us see why there is no effect of NO2 group if it is attached at the meta position. You can see this structure, para-nitrochlorobenzene. First step is very slow step, under which this OH minus attack on the positive carbon of the benzene. Then there will be a resonating structure. You can see there are three possible structure. When this OH, electron rich species, attack on the carbon attached with the halogen, then the electron density of the benzene that will shift to ortho position, then para position, then again become at ortho position, and your structure will be like this. You can see on your screen. These are the structures, and it will be your structure finally. And we get by the first step this OH derivative. It become your product. Now let us discuss. If it is at ortho position, then what will happen? At ortho position means its electron tendency to withdraw. Electron withdrawing tendency is more as compared to another position. This nucleophile OH attack on the carbon, then the electron density from the benzene ring that will shift at ortho position, and that will create the resonance, or you can say the relocalization of electron at ortho at NO2 molecule also. You can see in the structure. When these electrons, they will shift to this position, it will be the electron rich, and this electron tendency on the ortho position, that will be lesser due to the presence of NO2 group at the same position. And with the resonance, we get the product. Last step is the fast step. You know that the slow step is the rate determining step. But suppose when your electron withdrawing group is present at the meta position, then you will know that ortho and para position is the electron rich. So there will be no role of the NO2 to stabilize the electron rich position. You can see in the figure. Now, let us discuss about the nucleophilic substitution reaction of aryl halide. Due to the presence of NO2 group at ortho and para position, withdraw the electron density from the benzene ring and thus facilitate to attack the nucleophile on haloarenes. The carbon anion thus formed is stabilized through resonance. The negative charge appear at ortho and para position. With respect to halogen substituent is stabilized by NO2 group, while in case of metanitrobenzene, none of the resonating structure bear the negative charge on carbon atom bearing the NO2 group. Therefore, the presence of nitro group at meta position does not stabilize the negative charge, and no effect on reactivity is observed by the presence of NO2 group at meta position. Now let us discuss about the electrophilic substitution reaction by the halogen derivative. As most of the benzene derivative, they give electrophilic substitution reaction. Haloarenes undergoes the usually electrophilic substitution reaction of the benzene ring, such as halogenation, nitration, sulfonation, and Friedel-Crafts reaction is the best example of such type of the reaction. Further, substitution occur at ortho and para position with respect to the halogen atom. The ortho-para directing influence of halogen atom to be easily understood if we consider the resonating structure of halobenzene as shown. This is the resonating structure of halobenzene you are seeing on your screen. Halogen derivative. Halogens contain the lone pair electron and benzene has tendency to withdraw the electron. What happens in that case? The lone pair electron of the halogen that will shift toward the benzene ring and the ortho position and the para position that become the electron rich center. Due to resonance, the electron density increase more at ortho and para position than at meta position. Further, the halogen atom, because of its minus I effect, has more tendency to withdraw electron from the ring. As a result, the electron gets somewhat deactivated as compared to benzene, and hence the electrophilic substitution reaction in haloarenes occur slowly and require more drastic condition as compared to those in benzene. You can see on your screen. Chlorobenzene with Cl2 in presence of anhydrous FeCl3 gives us parachloro derivative and orthochloro derivative. So you can see the para position give most stability in the reactant. Similarly for the nitrogen, in presence of acidic medium, it gives us orthonitrochlorobenzene and para-nitrochlorobenzene. Para-nitro product is the major product. Similarly for the sulfonation. Friedel-Crafts reaction, it is very common reaction and the best example of electrophilic substitution reaction. When benzene or its derivative react with alkyl or acyl halides in presence of anhydrous AlCl3, that gives us derivative of benzene is known as Friedel-Crafts reaction. When chlorobenzene react with methyl chloride as given in the first reaction in presence of anhydrous AlCl3, you can see it will give us the 1-chloro 2-methyl benzene. That is a minor product, and when this CH3 come at para position, that become the major product. It is your major product. It is generally known as Friedel-Crafts alkylation reaction, and it is called the Friedel-Crafts acylation reaction when we used acyl halide as a reactant. In presence of anhydrous AlCl3, it gives us 2-chloroacetophenone, the minor product, and at fourth position, that means para, it gives us the major product. Although chlorine is an electron withdrawing group, it's a very interesting question for you to understand what happened when the chlorine atom attached with the benzene ring. The question is, although chlorine is an electron withdrawing group, yet it is ortho-para directing in electrophilic substitution reaction. Why? Now, think. Chlorine withdraw electron through inductive effect and release electron through resonance. Hence, inductive effect chlorine destabilize the intermediate carbocation formed during the electrophilic substitution reaction. You can see in the reaction. In the reaction, the ortho position, which is electron rich, the electron from that position attack on this electrophile, and you get the product. Similarly at the para position, and there will be no reaction on the meta position. Halogen tend to stabilize the carbocation, and the effect is more pronounced at ortho and para position. The inductive effect is stronger than the resonance and cause net electron withdrawal and thus cause net deactivation. The resonance effect tend to oppose the inductive effect for the attack at ortho para position and hence make deactivation less for ortho and para attack. Reactivity is thus controlled by the strong inductive effect, and orientation is controlled by the resonance effect. So it was the topic which we have covered in this video lecture. Please subscribe this channel, press the bell icon, and please don't forget to like my video lecture and comment also. According to your comment, I will provide you the more lecture. Thank you very much for watching.